All right, let's talk about something you're dealing with literally every second of the day, but probably don't know as well as you think. Today, we're diving deep into a force that's, well, fundamental to our world, but it's also packed with surprises. We're talking about friction.
You know, we all got the simple story in school, right? Friction happens when two rough surfaces rub against each other. All those little microscopic hills and valleys snagging on one another. But what if that's not really the whole story? What if that's just a tiny piece of the puzzle? Let's kick things off with a question that kind of turns that whole idea on its head.
So this is the picture of friction we all have in our minds. You know, two surfaces just grinding past each other, wearing down, getting hot. It makes perfect sense. It's what you feel when you're trying to shove a heavy couch across the living room floor. But this view, as we're about to find out, just can't explain what's really going on when things touch.
To really get how much our view of friction has changed, we've got to go back and look at the old rules, the classical laws that basically ran the show for centuries. Think of them as the first clues scientists found while trying to crack this everyday mystery. So the story really starts way back, over 500 years ago, with Leonardo da Vinci. But get this, his notes were lost for centuries. So it wasn't until the 1600s and 1700s that physicists like Amontons and Coulomb came along, rediscovered these ideas, and really started to formalize the rules of rubbing.
And what's so cool about this is how simple their tools were. Using these really clever devices, we're basically talking about blocks and weights and pulleys. And they came up with a set of rules that seemed to explain everything. And for a very, very long time, they worked perfectly.
And here are those rules. Okay, first, the harder you push two things together, the more friction you get. That makes sense, but then it gets weird. Second, the size of the contact area doesn't matter. Think about that. A car with wide tires has the same friction as one with narrow tires as long as the weight's the same. And third, friction doesn't care how fast you're going. These three rules became the absolute bedrock of engineering.
And this is exactly where those classical laws lead us to a really fascinating puzzle. See, if friction is all about roughness, then two perfectly atomically smooth surfaces, well, they should just glide past each other with almost no resistance, right? They should be pretty much frictionless. But as physicists eventually found out, that is not what happens. Not at all.
Okay, so let's get into it. To solve this whole smooth surface puzzle, science had to shrink, way, way down. This mystery actually led to the birth of a whole new field of science called nanotribology, which is just the study of friction, but on an atomic scale.
This just shows you the incredible leap in technology we're talking about. We went from the blocks and weights of Coulomb to amazing tools like the atomic force microscope. It has a tip so incredibly fine, it can actually feel the individual bumps of atoms. For the first time, we could actually see what was happening right at the point of contact.
And what we found was just mind-blowing. Even with two surfaces that look perfectly flat, the places where they actually touch are tiny, just a few little groups of atoms. And at those microscopic points, the pressure is astronomical. We're talking about 150,000 pounds per square inch. That is more pressure than you'd find at the very bottom of the deepest part of the ocean. And under those extreme, pinpoint pressures, everything changes. Those simple, elegant laws from hundreds of years ago, they just completely fall apart. Scientists realized that friction wasn't just one simple force. No, it was this complex, bizarre dance of forces all happening at the atomic level.
So, this is the big question. If it's not just about roughness, then what are the real culprits behind friction? What is actually causing that drag when one atom slides past another? Well, it turns out there are three main hidden sources.
This is gonna sound weird, but stick with me. As atoms from one surface slide over another, they actually jostle and vibrate the whole atomic structure of the material. This creates something called phonons, which are basically just tiny packets of sound energy shooting through the material. So the energy you use to push something is literally being turned into sound, and that creates drag.
And here's the next one. At the atomic scale, sliding isn't gentle at all. It can actually be a really violent chemical reaction. When atoms get close enough, they can form these temporary but really powerful chemical bonds with the other surface. Friction is the energy it costs to constantly make and then immediately break those bonds, over and over again.
Just look at this simulation. You've got a diamond tip sliding over a surface, and it's strong enough to literally rip a hydrogen atom away from a molecule. That's a chemical reaction happening right there. Every single time one of those bonds gets broken, it uses up energy. And that energy cost is a huge part of what we feel as friction.
Now, this one is especially strange. In materials that conduct electricity, like metals, the atoms are sitting in this sea of mobile electrons. Well, as one surface slides over the other, it can actually pull that sea of electrons along with it. It creates this kind of electronic resistance, another totally hidden source of friction.
And all of these things come together in a process called stick-slip friction. Basically, the atoms stick together, building up tension, and then they suddenly slip free, only to stick again an instant later. That jerky, atomic-level motion is what causes that awful jarring sound of nails on a blackboard. It's the atoms screaming.
Okay, so why does all this matter? Let's connect this deep dive into the atomic world back to our world. Because understanding that friction is sound, and chemistry, and electronics, that's not just a cool science fact. It actually opens the door to controlling friction in ways we never, ever could before.
Because we understand these hidden sources, we can start to design lubricants literally molecule by molecule to perfectly cancel them out. We can build almost frictionless surfaces for tiny little nanomachines, and the economic impact is huge. Friction and wear cost developed countries something like 1.6% of their entire GNP. This new science gives us the tools to finally fight back against all that waste.
So, after this whole journey from big wooden blocks all the way down to individual atoms, what's the new story of friction? Where do we stand now?
We've basically had to rewrite the old laws. Where the classic view said friction depends on the load, we now know it's the true area of atomic contact that really matters. Where it was independent of speed, we now know speed can have a massive effect. And maybe most importantly, we've gone way beyond just roughness to this much richer, more complex picture of sound waves, chemistry, and electrons.
But, the key thing to remember is that the story is not over. That's how science works, right? It's a process. Physicists are still working hard to build one unified theory that can perfectly combine all of these different atomic effects. The investigation is absolutely still ongoing.
And that really leaves us with one last, pretty exciting thought to chew on. The old pioneers of friction, they used blocks of wood and stone. We are now learning how to build things with individual atoms as our building blocks. With that kind of power, just imagine, what kind of nearly frictionless future could we design?